Okay, I'm going to do some momentum and impulse problems. Just to remind us, because we just learned this, momentum is symbol is P. So momentum is mass and motion, or also how hard it is to stop a moving object. And it's just mass times velocity. Then impulse is a force applied to an object over a specific period of time. So this is like a force applied for a time. It's not necessarily a net force on an object, like a sum of all the forces. It's a specific force that acts on an object for a specific period of time. And then we learned yesterday that if we apply an impulse to an object, we're going to change its momentum. So that is equal to delta. Remember, that's change in momentum, and that's usually going to be because of a change in velocity. So I'm just taking this equation, turning it into a delta version of it with a final minus an initial velocity, where that's the change in velocity that's occurred. And then the mass would not change. The mass is going to stay the same. Okay, so first question, calculate momentum of a 1,000-kilogram sports car traveling at 30 meters per second. This is pretty straightforward. We're just going to multiply m times v. That's going to give us 1,000 times 30. So this is kilograms. This is meters per second. And we're going to end up with 30,000 kilograms times meters per second. And that's just the units of momentum. They don't get, packaged up into something like newtons or joules. They're just what they are. Okay, so now what is the impulse needed to increase the car's speed? Okay, so there's some kind of force applied over a time that's going to happen to this car to increase its speed from 30 meters per second to 35 meters per second. So this means we're going to have a change in momentum that occurs. And so our impulse, and this is an important thing about this unit, because a lot of times students get hung up. They're like, well, I don't know how to solve that. You know the impulse is force times time, but we also know that the same impulse, this force times time, equals the change in momentum. What they're asking for here is just the product of this force times time, the impulse value, and that's equal to change in momentum, which equals mass times final velocity minus initial. And we know the mass of the car. This is the same car as in number 1. So we know it's a 1,000-kilogram sports car. We know that we want it to go from 30 meters per second to 35. So that means 35 is our final. And 30 is our initial. That's what we were starting at. So that's going to be 1,000 times 5. And that means our impulse is 5,000 kilograms times meters per second. So that's the product of the force times the time it's applied for to change this car's velocity, okay, and therefore change its momentum. So we took this massive object that was already moving, and now we've applied a force to it for a period of time, and we're going to make it move faster, okay? Okay, so then the same car, and it's now traveling at 35 meters per second, crashes into a rock wall. Yikes. And it comes to rest in 0.25 seconds. So how much force does the wall exert on the car? So now we're going to go back to, we've already calculated the change in, let me back up a step. We're going to go back to this equation, okay? Force times time equals mass times final minus initial velocity, okay? So now we've already got this is now our initial velocity. Okay, that was our final velocity in the previous question, but now this is going to be our initial velocity, and we're now going to come to a stop. Okay, so our final velocity is going to be 0. Mass is still the same, and they gave us a time. They want to know force, so we're going to solve this for force. And that means we're going to divide both sides by time. And we're going to get force equals mass times final minus initial velocity divided by time. That's going to give us the force that the wall exerted on the car. So let's see, I'm running out of room here. Force is going to be 1,000. That's my mass. So that's M times 0 minus 35, because I started off at 35 and then I'm coming to a stop, and I'm going to divide all of that by 0.25. That's my time. So a lot of the times in these type questions are short times, because you're applying, like I said, a specific force at a specific time period. And depending on the scenario, it could be a really short time that your foot is in contact with a soccer ball, or the club is in contact with a golf ball, or the car hits a rock wall and comes to rest. So, okay, so we got 1,000 times 0 minus 35. And then we're going to divide that by 0.25. So that gives us a pretty big number, 140,000 newtons. And notice it's negative, okay? Remember I said impulse is a vector, just like momentum. This is indicating to us that the force acting on the wall, the force acting from the wall, is in the opposite direction that the car was traveling in. So imagine the car's traveling along, and it hits this rock wall, bam, okay, the car is going to exert a force in this direction on the wall. The wall is going to exert a force back in the opposite direction, and that's why we get this negative. Okay, the negative is really coming from the change in velocity, because we were traveling at a higher rate of speed, and now we've stopped because we ran into the wall. So okay, so then last question, and then I'll do the next 3 in another video. How does the size of the force the rock wall exerts on the car compare to the force the car exerts on the wall? So wall on car compared to car on wall. And I try to give you a clue here. Which of Newton's laws of motion applies to your answer? So think about Newton's 3 laws. First one is object at rest stays at rest. Object constant velocity stays in constant velocity till acted on by a force. Second law, F net equals mass times acceleration. Third law is the kind of action-reaction type law. If an object exerts a force on another object, that object's going to exert a force back, equal value, opposite direction. So Newton's third law gets pulled into a number of momentum and impulse type situations, okay, especially where you've got collisions, which we'll be talking about more as we go through this unit. So the force that the wall exerts on the car is going to be the same value, opposite direction, that the force that the car exerts on the wall. Okay, so they are same value, opposite direction forces. So if we figured out that the force of the wall on the car is 140,000 newtons, then the force of the car on the wall is going to be that same 140,000 newtons in the opposite direction. And we can see that, through the diagram, through the way I labeled it, okay, in terms of direction. So, okay, so I will pick up in the next video because this one's about long enough.